Hello students, welcome to Soros's classes. This video is Inequalities Part 3. Now in the previous video we learned about what is inequalities and some of the elementary properties of inequalities. In this video we will learn about some of the theorems of inequalities. So let's start with theorem number 1, which is also known as arithmetic geometric mean inequalities. Now this theorem states that the arithmetic mean, this is greater than geometric mean when a1 a2 when a1 a2 so on till an, they are n distinct positive real numbers. So when a1 a2 so on till an, they are n distinct positive real numbers, then their arithmetic mean is greater than their geometric mean. In other words, the arithmetic mean, which is equals to a1 plus a2 plus so on till an, divided by n, which is our arithmetic mean. Now this is greater than a1 into a2 into so on till an raised to the power 1 by n. So this is our geometric mean. So our arithmetic mean is greater than geometric mean when a1, a2 so on till an, they are n distinct positive real numbers. Now here we're talking about only arithmetic mean and geometric means, but if we are to add another mean, that is harmonic mean, then the relationship is arithmetic mean is greater than geometric mean, which is greater than harmonic mean. So again, if a1 a2 so on till an, they are n distinct positive real numbers, then we will have our a1 plus a2 so on till plus an, this divided by n, this is greater than a1 into a2 so on till an raised to the power 1 by n, which is our geometric mean. This would be greater than n divided by 1 by a1 plus 1 by a2 so on till plus 1 by an, this is our harmonic mean. So our arithmetic mean is greater than our geometric mean, which is greater than our harmonic mean. Now if a1 is equals to a2 is equals to so on till an, that is all the n numbers and positive numbers are equal, then we would have our arithmetic mean would be equals to geometric mean, that would be equals to harmonic mean. So we can say that in general our arithmetic mean is greater than equals to the geometric mean, which is greater than equals to the harmonic mean. So our arithmetic mean, which is given by a1 plus a2 so on till an divided by n, this is greater than equals to geometric mean, which is given by a1 into a2 so on till into an raised to the power 1 by n, which is greater than equals to our harmonic mean, which is given by n divided by 1 by a1 plus 1 by a2 so on till plus 1 by an. So this is our theorem number 1. Now let us solve a question. So we have the following question where we have a equals to log base 5 3 plus log base 7 5 plus log base 9 7, and we have to find in what interval a lies. Now we are using the theorem, that is arithmetic mean is greater than equals to our geometric mean. Then from here we will have our arithmetic mean, which would be equals to, so arithmetic means of these three quantities, which is log base 5 3 plus log base 7 5 plus log base 9 7, this divided by 3, which is nothing but our a by 3. So a by 3, this is greater than equals to our log base 5 3 into log base 7 5 into log base 9 7, all of this raised to the power 1 by 3. So from here we will say that a by 3 is greater than equals to 1 by 2 raised to the power 1 by 3. Now why it is 1 by 2? Now see, here there is 5 is in base, but in the next term 5 is here. Similarly here 7 is in the base. So this product of log is equals to log base 9 and 3. So which is equals to log base 9 into 9 raised to the power 1 by 2, which is equals to half into log base 9, log 9 with base 9. So this part is equals to 1. So this part is equals to 1. So we will have our log base 5 into log 3 base 5 into log 5 base 7 into log 7 base 9. This is equals to 1 by 2. So our a by 3 is greater than equals to 1 by 2 raised to the power 1 by 3. So this would imply our a is greater than equals to 3 into 1 by 2 raised to the power 1 by 3. So the interval in which a lies, it would be 3 divided by 2 raised to the power 1 by 3 to infinity. So this is the interval in which a lies. Now we will go to our next theorem, which is weighted arithmetic mean, geometric mean, inequalities. Now if a1, a2, so on till an, if they are n positive real numbers, so if they are n positive real numbers and m1, m2, so on till mn, they are n positive rational number, then we will have m1 into a1 plus m2 into a2, so on till mn into an, all of this divided by m1 plus m2 plus so on till mn. This is greater than a1 raised to the power m1 plus into a2 raised to the power m2 into so on till an raised to the power mn, all of these raised to the power 1 by m1 plus m2 plus so on till mn. Now the left hand side is nothing but weighted average mean of a1, a2, so on till an, where m1, m2, so on till mn are the frequencies or weights respectively. So the left hand side is the weighted average mean and the right hand side is the weighted geometric mean. It is weighted geometric mean of again a1, a2, so on till an, where m1, m2, so on till mn are respective frequencies or respective weights. So the theorem 2 says that weighted average mean is greater than weighted geometric mean. So this is theorem number 2. Now suppose we have the following question where a, b, c are three positive integers, then a square plus b square plus c square divided by a plus b plus c raised to the power a plus b plus c. Now this is greater than a raised to the power x into b raised to the power y into c raised to the power z. Then we have to find the value of these x, y and z. Now let us first take the left hand side of the equation. So this is a square plus b square plus c square divided by a plus b plus c, all of this raised to the power a plus b plus c. Now if we take this part, now this is equals to a into a plus b into b plus c into c, this divided by a plus b plus c raised to the power a plus b plus c. Now taking this a as both the number and its weight, we will have from the theorem that weighted arithmetic mean is greater than weighted geometric mean. So a into a plus b into b plus c into c divided by a plus b plus c, this is greater than a raised to the power a plus b raised to the power b into b raised to the power b into c raised to the power c. So it is a raised to the power a into b raised to the power b into c raised to the power c, all whole raised to the power 1 by a plus b plus c. Now taking the power a plus b plus c on the both sides, that is raising both the sides by power a plus b plus c, we will get that this would imply a square plus b square plus c square divided by a plus b plus c raised to the power a plus b plus c, which is nothing but the LHS of our question. So this would be greater than a raised to the power a into b raised to the power b into c raised to the power c, thus into a plus b plus c divided by a plus b plus c. So this would cancel out each other. Now this LHS of this equation, say it is equation number 2, is equals to LHS of the equation in our question. We let us name it as equation number 1. So from them we can say that, so that is by comparing both the equations, we can say that our x is equals to a, y is equals to b and z is equals to c. So the value of x is equals to a, value of y is equals to b and value of z is equals to c. So this is obtained by comparing the equation from our question, that is equation number 1 and this equation number 2. Now let's go to our theorem number 3. It says that if a1, a2 so on till an, if they are n positive, so they are n positive distinct real numbers, that is a1, a2 so on till an, they are n positive distinct real numbers, then we would have a1 raised to the power m plus a2 raised to the power m so on till plus an raised to the power m divided by n. This is greater than a1 plus a2 plus so on till an divided by n whole raised to the power m. Now this will hold true if our m is either less than 0 or our m is greater than 1. So if our m is less than 0 or greater than 1, then what we will have is the arithmetic mean. the arithmetic mean of mth power of n positive quantities. So this would be greater than the mth power of arithmetic mean of n positive quantities. So this would hold true when our m is either less than 0 or greater than 1. Then arithmetic mean of mth powers of n positive quantities, this would be greater than mth power of the arithmetic mean of m positive quantities. And when our m would be between 0 to 1, that is when our m would lie in the range of 0 to 1, in that situation we would have our a1 raised to the power m plus a2 raised to the power m, so on till an raised to the power m divided by n. This would be less than a1 plus a2 plus so on till an divided by n whole raised to the power m. So what we will have is that the arithmetic mean of mth power of n positive quantities, this would be less than the mth power of arithmetic mean of the same n positive quantities. So this would hold true when our m would lie in the range of 0 to 1. Now in this question we are given that our m is greater than 1 and n is a natural number such that 1 raised to the power m plus 2 raised to the power m so on till n raised to the power m. This is greater than n into n plus 1 divided by k whole raised to the power m. So this is given and we have to find the value of k. Now from the above theorem we know that now since our m is greater than 1, then from the above theorem we can say that 1 raised to the power m plus 2 raised to the power m plus so on till n raised to the power m divided by n, this is greater than 1 plus 2 plus so on till n divided by n raised to the power m. That is, the arithmetic mean of mth powers is greater than the mth power of the arithmetic mean. Now this would imply 1 raised to the power m plus 2 raised to the power m plus so on till n raised to the power m. This would be greater than n into, now 1 plus 2 plus so on till n, it is the sum of first n numbers, so this is equals to n by 2 into n plus 1, this divided by n, so this got cancelled out, so this would be n plus 1 by 2 raised to the power m, so which is equals to our n into n plus 1 by 2 raised to the power m. Now if we compare now we can see that left hand side of both the equation in the question and this equation we have here is same. So now when we are comparing the right hand side, we get the value of k is equals to 2. Hence the answer is that the value of k is equals to 2. This is our answer.